Okay, let's just dive right into this explainer. Today, we're going to demystify the dense, formula-heavy concepts of thermal fluid sciences to see how energy truly powers our world. I mean, if you look around, everything from the refrigerator sitting in your kitchen to the engine in your car, and even those massive power plants lighting up our cities, they all operate on this beautifully structured set of physical rules. So what we're going to do today is translate those rules from complex textbook equations into clear, visual concepts you can actually use.
Here's our roadmap for the explainer. We'll hit 1, the science of energy, 2, 3 modes of heat, 3, the flow of fluids, and finally, 4, the chemistry of fire. Let's get right to it.
All right, pillar number 1, the science of energy. This is all about thermodynamics and the laws of nature.
So think about a hot cup of coffee for a second. Why doesn't it ever just heat up by itself? Well, this perfectly illustrates the second law of thermodynamics. Energy has quality and it always degrades towards a less useful form. You see, the first law tells us that energy is conserved, right? It can't be created or destroyed. But the second law asserts that actual processes always move in one specific direction. The high temperature, highly useful energy of your coffee degrades as it transfers to the cooler surrounding air. Now that energy is still there in the room, but it's lost its quality. It literally can't magically gather itself back together to reheat your mug. Now, when engineers are analyzing flowing fluids, they use a brilliant little concept called enthalpy to easily combine the internal energy and the energy needed to actually push the fluid forward. Think about a fluid moving through a pipe. It has its own internal microscopic energy. We call that U. But it also requires energy simply to maintain its flow against pressure, which is P times V. By combining these into a single property, enthalpy, engineers have an incredibly convenient shorthand to track the total microscopic energy of a flowing stream. Honestly, it makes balancing the energy of power plants and engines vastly simpler. And you know, this relationship between temperature and pressure is exactly why your beef stew cooks in 20 minutes in a pressure cooker instead of 2 long hours in a normal pan. We constantly say water boils at 100 degrees Celsius, but well, that's really only true at standard sea-level atmospheric pressure. If you crank up the pressure, like inside a sealed pressure cooker, the water needs a heck of a lot more thermal energy to break its molecular bonds and turn into a gas. That forces the boiling temperature all the way up to 134 degrees Celsius, which cooks your food in a fraction of the time. Conversely, if you go up a mountain where the air pressure is lower, water boils at a much lower temperature and cooking takes forever. Okay, moving right along to pillar 2, 3 modes of heat, or how energy moves from hot to cold. Before we get too deep into the weeds here, let's just set a clean mental checklist of the only 3 ways heat can actually move. All 3 require a temperature difference, and heat always flows from hot to cold. Conduction happens through direct particle collisions, convection involves the bulk movement of fluids, and radiation is the transfer of energy via electromagnetic waves. Let's look a bit closer. This is wild. Just look at the sheer data here. Diamond conducts heat so incredibly well that engineers actually use it to cool down highly sensitive electronics, despite the insane cost. Thermal conductivity measures a material's ability to conduct heat. Air is a fantastic insulator, which is exactly why we use foam full of air pockets in our walls. Copper is a great conductor, used all the time in pipes and wires. But diamond is on another level entirely. Because of its highly ordered crystalline lattice structure, it transfers heat almost 6 times faster than pure copper. It's a massive heat conductor, yet a poor electrical conductor, making it literally the perfect, albeit very expensive, heat sink for advanced tech. And notice the difference here when we talk about convection. Forced convection requires external work, like a fan, while natural convection relies purely on buoyancy forces. When you leave a hot-boiled egg sitting on the counter, the air touching it gets warm by conduction. That warm air becomes lighter and naturally rises, while cooler, heavier air falls down to take its place. That's natural convection. But if you blow a fan directly over it, you are forcing the fluid motion, which strips that heat away much, much faster. Now, it's absolutely incredible to think that radiation doesn't even need a medium to travel. I mean, no medium required. It's exactly how the sun's energy reaches the Earth across the vacuum of space. In engineering, we use a theoretical baseline for this called a black body. Basically, every single body above absolute zero emits thermal radiation. But this black body benchmark represents the absolute maximum possible rate of radiation a surface could emit at a given temperature. Real materials are just measured against this perfect standard using a property called emissivity, where a perfect black body is a 1. All right, let's jump into pillar 3, the flow of fluids. This covers fluids in motion and internal resistance.
So why is swimming so much harder than flying? Visualizing a fluid's internal resistance, what we call its viscosity, explains exactly why drag forces are vastly different for a shark swimming through water compared to an eagle flying through the air. You know, both water and air are fluids, but they have drastically different viscosities. Viscosity is essentially just the fluid's internal friction. Whenever a fluid moves against a solid body, or even when fluid layers just move against each other, this internal friction creates drag.
Okay, this is one of my favorite bizarre physical truths. Heating up a liquid makes it flow easier, but heating up a gas actually creates more resistance. It sounds backwards, right? In liquids, molecules are bound tightly by cohesive forces. When you heat them, they get energized, break those bonds, and slide past each other easily, kind of like hot syrup pouring way faster than cold syrup out of the fridge. But in gases, the molecules are already super far apart. Heating a gas makes those molecules move faster and much more randomly, which leads to more chaotic collisions. And more collisions simply mean more internal friction, increasing the gas's resistance to flow.
For engineers designing massive piping systems using Poiseuille's law, it really all comes down to this exact number right here, 16. Just 16. Why? Because doubling a pipe's diameter magically reduces the required pumping power by a factor of 16. In fluid mechanics, the pressure drop in a laminar pipe flow is inversely proportional to the fourth power of the radius. Practically speaking, this means if you simply double the size of the pipe, the resistance drops so dramatically that your pump only needs 1/16 of the power it did before. It's a profound mathematical reality that forces engineers to constantly weigh the upfront cost of buying larger pipes against massive long-term energy savings. Finally, Pillar 4, the chemistry of fire. We're talking fuels and combustion. Where does all this energy actually come from? Chemical bonds. Take a look at this theoretical perfect combustion, where exactly enough oxygen is supplied so absolutely no unburned fuel remains. In this ideal equation, we see carbon combining with pure oxygen to create carbon dioxide and a massive release of heat. Now, in the real world, achieving this perfect 100% theoretical combustion is nearly impossible. We usually have to supply a bunch of excess air just to ensure all the fuel burns. Otherwise, we risk incomplete combustion. And that's bad news, because it leaves behind soot, carbon monoxide, and a whole lot of unharvested energy.
Breaking and forming these molecular bonds releases vast amounts of chemical energy. This is literally the foundational math for running any combustion power plant. When we calculate the energy going into a system, we don't just look at the temperature, we have to look at the chemical composition. The enthalpy of combustion tells an engineer exactly how much thermal energy they can expect to extract when they burn a specific fuel completely.
And here's a huge efficiency hack. The phase of water in your exhaust actually completely changes how much usable heat you get out of your fuel. Whenever hydrogen in fuel burns, it creates water. If your exhaust gas is super hot, that water just escapes as a vapor, taking a ton of latent heat right out the smokestack with it. We call this the lower heating value. But if you can manage to cool that exhaust down enough to condense that water vapor back into a liquid, you capture all that extra latent heat for yourself. That's achieving the higher heating value, and it's a massive efficiency gain for any system. Okay, let's zoom back out for a second to this fundamental truth. Whether we are boiling water, pumping fluid, or burning coal, every single joule is rigorously accounted for, no exceptions. This is the first law of thermodynamics, the strict conservation of energy. It's the unbreakable rule that unites all four pillars we've covered today. You cannot create energy out of absolutely nothing, and you cannot destroy it. You can only master the art of converting it.
And that leaves us with a fascinating challenge. The physics won't change, but how we harness them absolutely must. As we look at alternative fuels like natural gas, ethanol, or hydrogen, we have to face the stark reality that they often have much lower energy densities than traditional fossil fuels. The laws of thermodynamics, heat transfer, fluid flow, and combustion dictate the exact boundaries of what is possible. The tools are all here. The question is, as the world shifts toward alternative fuels with lower energy densities, how will the thermal engineers of tomorrow reshape these four pillars to keep our world in motion?